Out of 20. So let's first talk about the quiz.
Yeah, that's
I think it was harder than I meant it to be. With that happens, yeah.
we forgive you.
The approach. Oh, Rogelio, you're here. I'm looking at yours. You weren't here when I. I'll still count your paper.
Why am I
But I didn't have a counting from the paper. Maybe we can do you have time right after class? I think you early till you can't come back.
so stupid?
All right, so the first problem asked for a Pythagorean triple where 7 was the smallest number. And I saw people make progress towards it and then scratch that out because when they got to the end of the thing, they saw, or the second page, they saw Plato's formula. Okay? And so you try to make that do. Maybe that's the mistake that I did, that I shouldn't have had both this question and the Plato's formula earlier. I should have had the other formula. The problem is that Plato's formula is always going to give you the smallest number is even, except if it's 3, 4, 5, or 4. But 7 is not even. So those of you who've used Plato's formula, you've got the other parts of a right triangle, but they weren't integers. And a Pythagorean triple has to be the whole numbers. So that's why that was only partial credit for that. How do you find something where 7 squared plus b squared equals c squared? So 49 is equal to c squared minus b squared. That's the way I was thinking about it. Remember the trick where you make the odd numbers add up to squares? I'm drawing a Pythagorean dot diagram. That's showing 5 plus 3 plus 1 equals 3 squared, right? Well, you just need to carry this out until the thing is 49 long. I don't know how many dots are in that. What is the odd number 49 going to? Where will we be if we're in the add 49 onto a square and get another square? In other words, the difference between c squared and b squared would be 49. That's the way I was expecting people to think about it. So that's the question. When is 49 the difference between successive squares? It's not too hard to get to it. Let's see. We've got to go fair distance out. There is a way to do this algebraically too. But the way I personally approached it was say, between 1 and 4 we have 3, and between 4 and 9 we have 5. Between 9 and 16 it's 7. So I just want to carry this pattern out until the odd number is 49, and what are the two squares here and here? You can just try to guess it. I mean, roughly how big should we be? We have to be over 100? We do? Well, let's see. 100 squared is 10,000. What's 101 squared?
I thought you meant the square. You have to go 100 to the square, so not over 100.
Oh, okay. Yeah. The square. So, have to be bigger than 10? Okay, 10 squared and 11 squared differ by 21. Not big enough yet. I don't know, 15? Can we do that? If I was at 15 squared, that's 225. And 16 squared. Can't do this in my brain. What's wrong with it? Usually I can do 16 times 16. You know how you do it actually? If you want to do mental arithmetic, you FOIL roll it. So 1 times 1 is, well, 10 times 10 is 100, and then 6 times 10 is 60, and another 6 times 10 is
Yeah, you should.
220, and then 6 times 6.
56.
220, 30, oh yeah, 256, I did that. That's the one I that one memorized. I should
It's the power of 2, right?
All right, so what's the difference there? Looks like 31. Oh, we're getting close. Up from there, how much farther do I have to go? This is what I'm suggesting here is a kind of a zero in on the answer approach. Well, actually, no, it's, because this is 16 squared. And I know the answer is 24 and 26, or 24 and 25. 24 and 25. So, if I thought maybe we have to get down, 30 is a nice number to square. 30 squared would be 900. 31 squared, again, foiling something that looks like a number plus 1, and it ends in a 1, isn't hard to do. Getting 900 plus 60 plus 1. So the difference there is 61. We've gone too far. You can do this kind of a searching around for it, or you can use systematic. But the eventual question, I think we found was 24 and 25 squared. Is that, some of you got it correct. Yeah, 24 and 25. What are those numbers? I don't want to have to foil one in my head anymore. Come on.
576,
Yep.
625.
Yeah, that sounds like they differ by 49, right? Okay, so 7, 24, and 25.
So you, don't also the numbers themselves add up to 49?
Oh, that's weird.
15 and 16 are 31. 30 and 31, 61. You just add up the numbers.
Wait, does that always work?
Yeah.
So wait, this is 3 squared and 4 squared?
No. Different by 7.
3 and 4 is 7.
Wow. Ah.
Well, I gotta leave this question on the test then.
Thanks, Devontae.
No, seriously, what if I ask you now, find a Pythagorean triple that's got 121 as the smallest number?
Oh, good Lord, I don't know how to deal with it.
Would it be 59? No, actually, that's not a good one. 123. I need some that I can break it into a number and its successor. Yeah. 61 and 62 adds up to, cool. So 61 squared plus,
You don't want it to add up to 123, I don't want that as 123.
oh, good point. Yeah, so I probably don't want to do that.
Yeah,
Still, I
then
think,
you would want
I
it
do
to
think
add up to
asking you to find a Pythagorean triple of a certain size is okay. It's just that the people that use Plato's formula, that kind of the wrong thing. You want the difference between, you don't want to have, that form forces the small number to be even.
Maybe the faulty assumption was that the Plato's formula finds all of them and not just some.
Right, and I fear that a lot of people have that thought, that Plato's formula together with Pythagoras' formula gives you everything. It doesn't. There's a thing that was discovered much later that does generate all the Pythagorean triples, but it's complicated.
Does it involve graphs and rotating the graph?
It involves finding two co-prime integers, m and n, and then using them to construct the triple. No, co-prime, yeah. One of them has to be odd, and one has to be even, but other than that.
So for this question, were you expecting us to use that reasoning with the dogs?
No, I was expecting lots of different answers. But what I was worried about, what I think happened is I misled people by having the Plato formula on there, and a lot of people got caught in a trap where they tried to use that formula, and it just isn't fun. So I was expecting people to actually do like guess and check kind of stuff, a little bit like what I was illustrating.
So what is the name of the formula for that? I don't know what this is.
Yeah, there was like an odd number formula.
No. Math experiment on this one. How did I have this?
Yeah, that's the Pythagorean version. Yeah.
There's a formula with the you calculate it with the odd and even numbers, right?
Yes, I can't hear what you're saying.
This was Pythagoras.
There's a formula where you calculate it with, like, if you're given an odd, there's a certain formula. If you're given an even.
I should probably have mentioned that too. I don't have my calculator with me.
Yeah, that's the
If you
formula
use your
I
calculator, you can put in x plus 1 squared minus x squared and hit the table. Just run down until you see 49. It's trivial to do that on a graph. Is that what you were suggesting?
No, it was in the book. It was in one of the problems.
Oh, okay.
It was like you're given n, then it's like 1/2 n squared minus 1 for odd numbers.
Oh, okay, that's what the.
That's what he. Okay.
Yeah, that's one of the versions of Pythagoras' identity for finding. What was the second question? Oh, yeah, this is the one where I really had a problem. So a triangle that's also equal to a square, and it said find the smallest one. One is a triangle number and a square number. That's what you drew?
Yeah, that's my fourth question.
That's the fourth question, I'm sorry, I'm getting ahead of myself. The second one was illustrate that the sum of two triangular numbers gives you an oblong number. And the basic, for n equals 4, I think this is the case here. So basically what you needed to do was draw the oblong number, and it's an array that looked like this. I'm not quite there, right? I've got a square number just now. One more row that has columns. And then divide it up. Perfect. That's all. So that most people were like halfway there and then didn't put the dividing line. But by putting that dividing line, you're saying, okay, there's a triangle down below, a triangle above, and moves that up to the top.
I just missed the question.
Was it poorly phrased?
I mean, you
I
just,
wasn't sure exactly what you
the
wanted.
sum, you would put plus sign. I see 2 times.
Oh, well, yeah. So a number added to itself is a sum.
Yeah.
You were looking for a doubling.
Yeah.
But doesn't this look like two copies of the same triangle?
Yeah, you just confused me now. You said sum, so I was like, wait.
So that it became obvious when I said it as a sum, when it was hard when I said it as a doubling. That's fair.
Even when I left the voice I said, I'm not sure if I did the second one right, because I'm not sure what you wanted. But I just drew the oblong shape.
Yeah, I wanted a little more than just the oblong
Yeah.
shape. But I gave partial credit for the oblong shape.
Just saying I didn't understand it because
You can complain if you want to. That's fine. But that's, with partial credit, there's always an argument of how much.
one more point.
One more point. So the third problem, everybody got. Okay. I don't think I've seen a person get that. That's good, because it was just a formula, you would plug into it and then verify. Oh yeah, no, wait, there was one person who didn't do the verifications. But I took.
What was I supposed to do?
You're supposed to actually square the two smaller numbers and add them up and verify that it equals the square of the bigger.
Oh, okay. Yeah, I forgot about that.
And then the last one was that 1 is equal to 1. 1 is a square and a triangle. That's not the answer that I had in mind. Devontae came up to me during the quiz and like, this, yeah, and it was like, yeah, that really is it. I was thinking 36. But 1 is 1, and it's both a triangle and a square, so that's totally right if you said that. The only way to find it is, I think, by just kind of brute force. List down a bunch of triangles, numbers, instead of a bunch of squares, look for where they collide.
You don't really have to listen to the square numbers if you know your basic square. You can just look at the triangles until you get the number that
That's
you know
true.
is a square.
Yeah, you probably know your squares up to, I was going to say 256, but maybe not.
10 or 12 easily. And then
12 is a gross, right? 12 squares is 444. Yeah, 11 squared? Yeah, so you wouldn't have to go very far before you run into 36 as a triangular number and go, yeah, I recognize that as a square. Although there was somebody who got to 10 as a triangular number and said, oh, that's a square. Brain failure? I don't know if that happens, right? Yeah, so I got something on the top. Anyway, so that's for the quiz.
So doesn't Plato, the triangle thing, doesn't give you triangle and squares along both diagonals? I'm drawing there, I couldn't get it.
No, the other diagonal of the Pascal triangle is more figure numbers. There's no squares. There's tetrahedral numbers. There's we don't have a good name for the 5-dimensional solids.
Right, that's how it's.
Pentachloron numbers.
Do you ever use 5-dimensional objects for anything? I know sometimes you can use four-dimensional objects for some of your applications, but never five-dimensional.
Well, hypercubes of all dimensions get used in computer architectures. So, and that is actually one reason for studying high-dimensional things. The point is to have a whole bunch of processors that are massively interconnected, but you don't want to connect every processor to every other processor. That's too much communication. So you come up with comm schemes between networks of processors that are often laid out in hypercube geometries, but there's other things too.
Okay.
There's some use to it. There is, I mean, you know, also, I think just natural curiosity. Like, the Greeks saw these 5 platonic solids. It was early in the 1900s that somebody finally classified all the 4-dimensional regular figures.
Are there more or less than three-dimensional ones? Or the same?
It's 6, and then 5, and then 3 forever.
Yeah, it's 6 in 4 dimensions, in 5 dimensions. No, it's 6 in 4 dimensions, 5 in 5 dimensions, and then just the cube, the simplex, and its dual. The cube's dual. Okay, where are we? We're almost out of time, and I haven't even put the slides up.
Well, it's because you're going to need to go over that thing in case that part's in case you have one of those questions on the exam. It wasn't good use of time.
Yeah, I suppose.
You're not being abused.
I'm not being away.
We're being kept, watched.
Yeah.
Not today.
Sounds good.
Okay, you guys know this already. The fourth paper, or the second paper due today, fourth paper will be a 3-page deal. A review of a mathematical movie, mostly like 2/3 of it probably should be commentary on the math content of the movie. Whatever it is. Have most people who got a film already watched it? And I also have not put up the list of what all of them were. I'll get that probably this evening. We've got the Friday the 13th midterm.
How would you put a midterm on Friday the 13th? Who
Because
would
we
want that?
asked for it, shush.
I left something off when we talked about our communities, and I felt bad about this after class, and I was like, okay, I gotta fix this. And so, because it's considered one of the sort of cool, great problems of Greek mathematics, and the fact that our community solved it is too. So here's the question. We've got a particular ratio in mind. I'm saying it sort of from the end here, where the statement is finding something that is equal to a specific ratio. You want to think about that ratio as in your head to begin with. And the idea is to slice through a sphere so that the 2 parts of it are in that ratio. So how can you do a thing like that? I'm going to show you that by referring to our textbooks. They have a nice little report up there. Page 198. Oh no, I'm on the wrong page. The page is like a gray blurs me right now. It's like not having my eyeglasses on.
Do you want to borrow mine?
Well, it's your prescription.
Not the same source.
Yeah, I don't know. Yeah. Oh, I lost it. Yeah. Can you see that? I'm gonna zoom in. Not that much. Book 2 on the sphere and cylinder treats this problem. So, actually, proposition 4 of book 2, which actually poses one of the great problems. I already said that. Pass a plane through a sphere in such a way that the volumes and the segments cut off are in a given ratio. So they ask, there's this modern analysis of it. This would have been available to our meetings because you wouldn't have variables yet. I think it unlikely that people know this formula. Do you know the volume for a portion of a sphere?
Not at all.
You may have seen that in related grades, sure. Filling a spherical tank, the amount of liquid that's at any point is, has a height, right? And then the rate of change of that volume related to the time derivative of the, yeah. Okay, so you may see that. The quick way to derive it is to do a Calc 3 surface of revolution type integral. I'm not going to, but that's the formula. You can check it. Notice that what degree polynomial is that if you think of h as the variable?
33.
So we're trying to get that this one, oh wait a minute, those are not the same. Okay. So what has happened to go from that one to this pair that are in relation to one another? They have times by 3 inside there. So we get, instead of r minus h over 3, we've got 3r minus h. That's just multiplying by 3. It's fair to do that as long as you do it in both top and bottom. Oh wait, you're dealing with a simpler thing. You don't have fractions within their polynomial. They've also, what else have they done? They've gotten rid of the pi's. It's fair to do that too. Canceling off the same thing we're talking about. So we get these two degree 3 polynomials, and the ratio between those polynomials is equal to n. Notice they're in different variables. A squared, and h in the top, k squared, and k in the bottom. What we actually do know is there's a relationship between h and k. They're not totally independent of one another. If you've taken a sphere and sliced it up, the height of one portion, the bottom portion, and the height of the top portion, those heights add up to the total diameter of the sphere. That's what they're using right here. H plus k is 2r. So, solve that. I have to check which one they solve it for. H squared 3r minus h times n. That's just cross multiplying. The other side is m and this guy. I've got k squared. They've got 2r minus h squared. Ah. Yeah, right, that's because h and k add up to 2r, so this thing, 2r minus h, is what 3? Good here? Yeah, so we have to, that's what we need to work out. Why is 3r minus k actually equal to r plus h? That's fine. To erase. Just remember, there's always a glare in the videos. There's what you guys here. Right, so we had 3r minus k, and replacing the k with 2r minus h, we get 3r minus r minus h. That's r plus h. Is that what we got in here? R plus h. Awesome. And then they foil rolled it. You can't foil roll that directly. You have to first foil out that one, and then you have to multiply it by that one. Anyway, that's the product of two polynomials, so we can do it. The thing to notice is, what's the degree of the problem here? We've got degree 3 in h on that side, degree 3 on h on that side. There's no way to get it other than to be able to solve a cubic equation. Do you know how to solve a cubic equation?
Isn't the formula like 3 pages long?
No, it's only like half a page.
Big difference?
The general thing, I mean, the quadratic formula is so easy. You get theta b plus or minus square root b squared minus 4ac all over 2a. Okay, maybe not that easy. My Math 120 students have a real hard time with that.
Well, that's how I memorized it.
I sing it in song form, and they're like, yeah, that's
Have them prove it by completing the square abstractly.
what I'm doing today.
Oh, awesome.
The formula for the cubic equation exists, and it was discovered in like the 1600s. Gary, I've forgotten the name. So it's hard, and then somebody was able to write a general formula for the fourth degree equation. That's the one that's like 3 pages long. In general, an equation has as many solutions as its degree. Quadratic has 2 solutions, linears just have 1 solution, cubics have 3 solutions. What Archimedes did with this is kind of a genius thing. He realized that he could solve this cubic equation by actually intersecting 2 things that are quadrats. So the approach that he took is to intersect a hyperbola and a parabola, and knew that the point of intersection was going to be the same thing. It's going to be the solution to this problem. So it's a clever reduction, and it's a geometric way of solving it too, which is kind of neat, right? The modern approach is to use the formula or actually use numerical stuff. Often we solve higher degree polynomial equations by starting with a guess and then having an iterative approach that draws you closer and closer to the solution. Have you guys ever used your graphing calculator to find like the intersection between 2 curves?
Yeah.
So usually it says first curve, and you go this one, okay? And then the second curve, this one. It always asks you to guess next. And most people just go, I don't know what to guess, and they hit enter. But if you have curves that are intersecting in multiple places, that guess is important. You want to get close to the point of intersection with your initial guess. But that's the modern approach. It's computer out. It's using computer tools. There really is no solution in general to this problem. If you have high degree polynomials, like anything degree 5 or greater, there is no way to write down a closed formula for it. That's right. So that has to do with group theory.
But we've shown that it is indeed impossible, not that we just haven't found a way to do it.
No, it's literally impossible. This is probably one of the most romantic stories in all of mathematical history. We'll get there. We're going to talk about this at length, but it's a French Revolution period. Maurice Galois was this mathematician who, he was 19, got challenged to a duel. And he knew he was going up against somebody who was going to kill him the next day. So he spent the whole night writing out his mathematical things, one of which was what is now called Galois theory, and eventually led to the realization that solving things in radicals had to do with the symmetry group of the equation. It's called the Galois group. And if the group has certain properties, you can solve it in radicals. But most often, when the degree is 5 or greater, the group isn't going to have those properties, so it's not going to do it. It's an abstract algebra connection you will rarely get to in an abstract algebra undergrad course, which sucks. Because it's like the gem. It's the cool moment at the end of undergrad abstract algebra, and most often you don't arrive at it. So take a graduate abstract algebra course, and then you get. So that's what I wanted to make sure I didn't skip over entirely this division of the sphere into specific ratios. Okay, talking about Hypatia in the last 10 minutes, which is probably going to be enough, because we honestly know so very little about her life that there's not much to say. We have the book very accurately, with no question mark on it, says 370 to 415. Totally don't know that. We don't know how old she was when she died, really. She could have been in her 30s, she might have been in her 50s. So there's a lot of different estimates out there. And that she was born in 370 also, just an estimate. I don't know if you've gotten used to seeing people's birth and death ages in reverse order, because we were dealing with BCE before, but this is in the 4th century AD. Is that how you count them? The years 0 up to 99 were the 1st century. Okay, so yeah, that's the. She died, I guess, in the 5th century. That's
So, why was the whole thing about common era and after that? Why did they change that?
well, Anno Domini is what AD is an abbreviation for. And BC stands for before Christ. And people feel this is too Christian-centric. It's sort of putting down, it's a Western, what's the word? Monoculturalism. We're trying to impose this sort of Western tradition on the rest of the world, and in the modern era of political correctness, that wasn't cool anymore. So we started, I figured, let's leave BC mostly alone. We'll call it before the Common Era, BCE, and then Common Era for the years we normally use instead of AD. AD is Anno Domini, which is the year of our Lord in Latin. Anyway, look back to Hypatia. She wasn't just a mathematician. I think like most of these Greek philosopher, mathematician, scientists in Alexandria, she did a lot of things. One of her big interests was astronomy. But philosophy is actually what her major mark was in. She was the head of a Neoplatonist group. In astronomy, she was the editor for probably the most famous astronomy book up until Kepler. So Claudius Ptolemy. You recognize that last name, Ptolemy? That was one of the generals from Alexander the Great, and his dynasty took over Egypt. Now this is just some distant relative of General Ptolemy, but still having that name said something. He wrote this book called the Almagest, and apparently he wasn't a good writer. So Hypatia took it and straightened it out, and corrected all his errors, and turned it into a really good book. And it turned out to be a famous book for a long, long time. But it is not the truth about astronomy. You have to think about how people in the ancient world thought of astronomy. Way different from what we think. What's the center of our universe?
No, it's of course the Earth.
Well, now we know it's actually, it's a stupid question. The universe sort of has no center. If you want to think four-dimensionally, the center is the Big Bang. Okay, but to them, they were just thinking about the observable universe. For them, that was the Earth and the planets that they could see, and the sun and the moon. And the obvious, I think it's obvious thing to start off with is the Earth must be in the middle. Especially if you have a religious viewpoint. Either you thought the Greek gods created the Earth, or Earth was the body of Gaia, and it's the sky god. I can't remember.
Uranus?
No, that's his son. He's one of the Titans. Uranus. Say it Uranus, by the way. Before it's a whole.
Why can't we say Uranus?
You know the show Futurama?
Yeah.
They did this gag in there once where they said we changed the name of the planet to Erectum to avoid those jokes. Uranus is actually how the Greeks said it, so I'm going to go with that. He was the sky god. Gaia was the earth goddess, and the two of them got together and they had lots of little babies called the Titans. And then there's an event called the Titanomachia, where the baby gods and the Titans fought, and the baby gods won over the Titans. Anyway, that worldview with the Earth at the center, what are those planets doing out there? And what is the sun doing? They assumed there were crystalline spheres, because it's the universe. It's created by either the one God, if you're a Christian, or the many gods, if you're not. It had to be perfect. They couldn't accept the idea that things would travel as we now know in elliptical orbits. So they knew those spheres were perfect cylinder. Those spheres, perfectly circular. But then when they looked at the planets, they weren't moving as if they were on perfectly greased tracks on a circular thing. The planets do some funny stuff. There's a little loop-de-loop that most planets do. Have you ever heard about this?
Isn't that like a also more in line and Pluto's like that?
No, that's a different issue. Pluto's orbit is strangely misaligned with the rest of the planets, which is one of the reasons why he could have voted for planethood. But no, the problem I'm trying to talk about is called retrograde motion. So if you've got a planet that's outside the sun from you, like Mars is, for instance, think about this as a sort of racetrack. So I'm on the inner track on the Earth, and I'm going fairly rapidly. Mars is on a more distant track, and it's going slower. Right? And sometimes of the year, it'll appear that Mars is going around me this way. But if I get to the point where we're sort of across from one another on those racetracks, for a minute, because I'm going faster, I see Mars going backwards. So the track of a planet literally has these little curlicues on it. Why have I no markers anymore? If you look at it, if you track the path of a planet through time, you'll see that it kind of does this little thing like that, where you'll see, that's called retrograde motion. So they needed to explain that. What Ptolemy said was, well, on the spheres that the things are moving, there's other spheres. So what do we now call epicycles? I don't believe Ptolemy used that word, but you have basically a circular frame that the planet's moving on, but that's not what the planet's moving on, that's what the epicycle of the planet is moving on. So he posited the idea that here's the Earth, there's a circle for, say, Mars, but that's not really what Mars is on. Mars is on another little circle like this, and as it rotates around this big circle, it also spins on a little circle. And you can account for retrograde motion that way. And you can account for some of the abnormalities of planets that are inside of the sun to us. They did know about Mercury and Venus in those eras. And their orbits are elliptical. And you don't see the retrograde motion there because they're interior to the sun from us. But you still can tell that there's funniness business going on with the motion. Where's the sun and the moon in this business?
The sun,
Yeah.
the sun's rotating around Earth.
Yes, it's rotating. Does it need an epicycle? No, it doesn't. Because really, the Earth is going around the sun, and that motion is relatively uniform. It's almost perfectly circular orbit. So the sun was one of the exceptions. It didn't need an epicycle. And then they had to deal with the moon, which is clearly going around us. Right.
Does it have its own epicycle and is it epicycle?
I think the moon needed an epicycle in some of the refinements, not in Ptolemy's original thing. Because the moon's orbit is elliptical, but only a little. It's very close to circular. The thing that got her in trouble was this. She was the head of the Neoplatonist school of philosophy. She was regarded, not like officially the head, just like she was the primary scholar who posited these ideas. And these ideas were not cool with the early Christians. In the first couple of centuries after Christ, Christian religion was pretty militant. Right? They were trying to spread their ideas. And not at all what we think of Christian values now, which is turn the other cheek, kindness to your fellow man. And stuff. No, if you weren't towing the line and believing in Christ, you were going to be beaten up, maybe worse. I gotta mention this, because we always talk about her as being the first female mathematician. But remember when we talked about the Pythagoreans, they were cool with women being in their numbers. There were something like 30 females in the Pythagorean brotherhood. There was this woman named Theano, and various accounts said she was his wife, was his star pupil, and then later people thought maybe she was his daughter. But definitely a brilliant mathematician, a great mind. We just don't know quite what she did. Because again, with the Pythagoreans, they were very secret. And there were other women too, but the problem is nobody was like known by their name until Hypatia. So Theon of Alexandria, I was going to do this whole gag where I explained how Theon became the ward of this other planet, Stark.
Game of Thrones?
I think the guy who wrote Game of Thrones was a fan of like history of math. There's a bunch of names for Game of Thrones that are Theon. Yeah, probably so.
A lot of Game of
Theon was the chief of the institute. And the other thing we know about Hypatia is her main mathematical study was 5 sections. I meant to get I had just too many props with me today, so I couldn't do it. But we have a nice version of this in the math, what do we call it? Manipulator's lab. It's a beautiful wooden cone that is sliced in a bunch of different ways so that you see the way you can get cross sections of a cone. And you'll get ellipses, circles, parabolas, and hyperbolas. And it turns out those sections through a cone are also the types of things you see in orbits in space travel. Comets follow hyperbolas. a body in motion in a uniform gravity field. It's kind of an orbit. It's a parabola. You know, the planets move in elliptical paths. These are the things she studied. But she got in trouble because the Christians and pagan thing. I'm really out of time, but let's just talk about this last thing. In the Burton book, he gives the statement that the hands of a mob, you know, these Christian militants didn't like that she was supporting the old gods, cut her with sharp oyster shells and then dismembered her. Literally cut her so that her joints were weakened and then pulled her up. Either with a group of people or with horses, I don't know. I mean, it's hard to pull a human being apart. And she was mostly like a 50-year-old lady at this point. It's just horrific. I can't imagine that they were other people have said they burned her at the stake. So he said they took her parts later and burned them. That was the standard punishment for witches. They considered her a witch. So that's the end of Hypatia. And it's also the end of the Greek Golden Age. That's pretty much, we're done with Greek mathematics once Hypatia's now. Soon after that, like 100 years after that, the Library at Alexandria was gone. Then there was a Muslim invasion, and they took what few shreds of it were left, and really, so I mean, nothing is left of what was in that beautiful library. Imagine where we would be today if all that knowledge hadn't been lost. And you know these writers. Do I have anybody who does not put their corrections and or their paper